Hello and welcome back to Calculus 2, section 10.7 on root and ratio test. So we're going to talk about factorials first, then ratio test, then the root test, and then we're done with this lecture, not with the day. So we'll first talk about factorials. Factorials are, well, here's the definition. N factorial is 1 times 2 times 3. So you multiply all of the integers all the way up to n. So you keep multiplying. So what is, and I'll put this in the cloud. There is a notation that no one uses. I mean, a lot of people use it, but no one uses it in calculus. You can also write n factorial is equal to pi. N goes from 1 to, no, sorry. I goes from I to n of I. So when you have a summation, it's addition. When you put the pi, it's multiplication. It works the same way as summation notation. Instead of sigma, you put pi. You will not see this unless you take advanced math courses, okay? But I just wanted to put it there on the side, so Thanksgiving is coming up. You can bring it. You can bring that stuff up. Okay, so what is 6 factorial? It's 1 times 2 times 3 times 4 times 5 times 6 equals to 720. Bueno? Now, do you notice that this over here is a 5 factorial? Yeah, right? So we can write 6 factorial as 5 factorial times 6. We can also write it as a 4 factorial times 5 times 6, which is times 30, right? And whatever, 3 factorial times 4 times 5 times 6. So you can break them up in any way. And the fact that you can peel off factorial like this gives us the formula that n factorial can be written as n minus 1 factorial times n. And this formula is useful for our ratio test coming up, and chapter 11, and then differential equation chapter 3, and so on. This formula is crucial. Now you are going to see this mainly in the form of n plus 1 factorial is equal to n plus 1 times n factorial. Most of the time you're going to deal with this one, so I'm going to put this one in this purple cloud. This is simply peeling off the extra term to leave it on the n factorial scale. Now, technically, if your n is equal to, let's say, 10, then 11 factorial is 10 factorial times 11. Or you can write it as 11 times 10 factorial. Whatever, they're commutative, you can write either way. So this is a little intro on factorials, because we use factorials. This is a discrete function, and we know that in terms of, well, maybe you don't know, in terms of the growth rates, it falls in between exponential and n to the n. So if we talk about growth rate, so growth rates, we have the sluggish one, which is ln n, grows slower than some n to the p, grows slower n to the p times ln n, grows slower than b to the n, grows slower than n factorial, grows slower than n to the n. And this is what we used it for. We know that when limit n goes to infinity, if you have a mismatch of type of functions, then you can just look at which one grows faster and come up with the answer. So if you have fast divided by slow, then you get infinity. I'll put this in quotation marks because this is not mathematically correct notation. And then if we have slow over fast, right, then it's 0. So if I quickly want to find the limit of n factorial divided by 3 to 100n, like this, as n goes to infinity, I know immediately that the answer is infinity without doing any math, because n factorial grows faster than exponential b to the n. I don't care that there is 100 there. You can have 1,000,000. It will eventually win. Yes.
What about the square root? What about the square root of it?
Square root is in the category of n to the p.
Oh.
Because it's 1/2 or 3/2 or 7/3. So it's going to be, your square roots are going to fall in here. Faster than log, slower than exponential. Faster than log, slower than the polynomial, and definitely slower than exponential. Or if you have this 100n looks like loon, so I'm just going to change this into, let's say, 98n. There we go. So it doesn't look like loon anymore. Whatever loon is, but limit n goes to infinity of, let's say, 49n cubed divided by 2n plus 1 factorial is immediately equal to 0. Again, because n factorial grows faster than polynomial. So the reason why you study and remember the growth rates is so you don't have to deal with calculations when your limit goes to infinity. Now, if you pin factorial against factorial, you will have to check. If you pin function composition against any of these, you have to check. Can I make factorial grow faster than n to the n? Yes, I can, if I use function composition. Because if I use n factorial in the exponent of b, oh yeah, it's going to win. Okay? So you have to be very careful with these things. These methods here for limits are going to work only in their vanilla state, which means no function composition. You can add them, subtract them, you can do whatever you want, and something is always going to win, right? But when you start doing the function composition, you can change the outcome of that, because again, then it's two functions against one, that combining the powers, right? So you have to be very, very, very careful. So n to the n is the boss unless there is a function composition. And if there is function composition, it could lose. I mean, it could still win, but then you have to use the limit. Now the question is, well, how do I do the limit? L'Hopital rule. Yeah, it's your friend, right? From Calc 1. 4.7. If you don't remember, I taught it earlier today. So you just need to look at the latest video I had before this one, right? And there will be L'Hopital rule to review 4.7. Okay, cool. So that's all about factorials, and we inserted this growth rate so we can take the limits, and we are now ready to talk about ratio test. Okay. So first thing, we are going to review this in about an hour or so, but the test that you should try against every problem you ever see first is clearly your divergence test, the n-term test, the first row. So that one you immediately try, and that one can spot some of the divergent series very quickly. But that's not the most important test of all. The most important test of all is actually ratio test, right? So ratio test is going to be used later in chapter 11 to figure out the radius and interval of convergence of power series. And ratio test is pretty much the only one you're going to see later on when you deal with sequences of series down the line in your other courses, let's say maybe in discrete math or some of the other courses, including your computer courses, engineering courses, and so on. So ratio test is the boss, and ratio test has a very simple rule which says you have some series an going from, let's say, 1 to infinity. You can start at 7. And you have this limit of absolute value of an plus 1 divided by an as n goes to infinity. This one can spawn 3 different answers. Less than 1, converge. More than 1, diverge. Equal to 1, test is inconclusive. So you have to use something else. And this is it. You're done. So put this on a cloud. It's on your sheet already. And this is your ratio test that you get to use also in chapter 11. Now, I'm going to add a sentence. If the problem contains n factorial of some kind, use ratio test. This is the only test that is to be used for factorials. Can this work with others? Yeah, it works with geometric, it works with a lot of other stuff. But if you have factorials, the only test you can use is ratio. So that's how you immediately going to spot when we do the overall all of possible tests, right? As soon as you see factorial, oh, this one is a ratio.
What if you do the limit and the answer becomes 1? Answer is 1.
Then you have to use a different test. Now for factorials, they grow quickly. So something is going to win out, right? When you have factorial against factorial. And then when you have factorial versus something else, again, you're going to go. So you don't have to worry about getting the situation where you're going to have a factorial and get the answer of 1. But there are always numerical methods, right? Or giving up. It's also an option. All right. So let's take a look at ratio test. We're going to test this on the familiar problem. Summation 1 to infinity of 2/3 to the n. What do we know about this problem already? I heard word converges. You have to talk more. Because if you just say converges. Okay. So this is, if you want to talk exam 3 right now, I'm going to give you the scoring on the test for exam 3 regarding this particular answer. When you see this and you write converges, that's 2 points and then -8, right? If you say converges by geometric test because r equals 2/3 less than 1, that's 10 points -0. Both of these answered converges.
What if you just say by geometric test? Like converges by geometric.
Okay, then what's -4? All right. So do we all understand the difference in the answer? This one could be a 50-50% guess. This one is a respectable answer. Now, this is all cool. This is all correct. It's not what we need now. I'm very happy that you know that this problem converges by geometric test. We are going to also solve this problem now using a ratio test. So thank you. Now, an is given as 2/3 to the n. I need an plus 1, which would be 2/3 to the n plus 1. Limit n goes to infinity. These absolute values are not here for decoration. And you will see why in chapter 11. So get in the habit, ratio test, boom, absolute value right away. So absolute value of an plus 1 divided by an. This is ratio test. So your job now is to work this out. What do we have? Well, in order for me to work this problem out, I need to peel off the plus 1, the extra exponent. So what I have is 2/3 times 2/3 to the n divided by 2/3 to the n. Do we all see what happens? Cancelled. And immediately we have answer as 2/3 because all of the n's cancelled. We have nowhere to plug this infinity, so the answer is just 2/3. That's less than 1, converges by ratio test. And obviously it has to converge because we already know, right, that it converges by geometric series test. You can't have, right, two different tests give you two different answers. One gives you convergence, the other one gives you divergence. I mean, right, that would be absolutely absurd. So we knew that. Awesome. Let's see what happens if I have summation 3 to the n. Let's start at, I don't know, 2. What do we know about this problem? Excellent. Can we do that a little bit faster? Yeah, we can. Diverges by the first test you always try, and that is the limit is not 0. The limit is infinity. Therefore, it diverges by the divergence test or the n-term test. And now we're also going to show it's going to diverge by ratio. So pick your poison, right? So already we know it diverges. Cool. An is 3 to the n. An plus 1 is 3 to the n plus 1. Stuff this into the limit and goes to infinity. Absolute value, 3n plus 1 divided by 3 to the n. Peel off a 3 to have 3 to the n to cancel with 3 to the n. And the limit is 3. Larger than 1, diverged by ratio test. So I hope you understand the way test works. Your job is to extract an, make an plus 1, stuff that into the limit, and work the limit out to get less than or larger than 1. If you get 1, the test is inconclusive, you have to use something else. Now, something else might or might not be available. We saw that in this case, we show divergence by 3 different tests. We did a divergent test, geometric series test, and the ratio test. They all show divergence. The upper one was just geometric and ratio to show convergence. Great. But these are not the problems that we have this test for, because, right, we have others. We would like to see some problems that involve factorials, right? So how about if I have a problem which mixes 2 to the n with n factorial, like this. Start at 1, go to infinity. Right? So you look at this thing and you say, the first thing I'm going to try is always divergence test. The limit of exponential function divided by the factorial, exponential is slower than factorial, faster function in denominator is 0, limit is 0, right? So divergence test doesn't work. Great. So we go and we do ratio. So an is equal to 2 to the n over n factorial. An plus 1 is 2 to the n plus 1 divided by n plus 1 in parentheses factorial. So now, limit n goes to infinity, absolute value of 2 to the n plus 1 over n plus 1 factorial divided by 2 to the n over n factorial. And the rest is algebra. You have to peel off factorial using the factorial formula in a purple cloud, and then you also have to peel off the 2 from the exponent. Cancel, and you're done. So we have 2 times 2 to the n divided by n plus 1 times n factorial divided by 2 to the n over n factorial. And now you can take the double fraction and write it as a multiplication when you flip the denominator, right? So you have 2 times 2 to the n over n plus 1 times n factorial times the flip of the bottom, which is n factorial 2 to the n. I know that some of you will immediately write this, which is okay. It's fine. So now what do we kill? 2 to the n and 2 to the n, gone. N factorial, gone. And we are left with the limit. N goes to infinity. All the values that stay are positive, so there is no need for absolute value anymore, because your input numbers are 1 to infinity, and all you have is n plus 1, so you can't get that negative anyway. And that's it. The limit is 0. Ratio test says when it's less than 1, converges by ratio test. Does this make sense? Yes?
On the test, if you just say convergence by ratio test, you'll get 6 points. And then, right?
No, you have all the calculations. I see 0 less than 1. Everything is cool.
Oh, okay, got it.
If you want to write the full sentence, I mean, I'll like you better, but the the trick is I already see 0 less than 1. You're writing converges by ratio test. I know that you know which test you used. I know that you showed the conditions of convergence, right? So it's a full credit. But if you want to write the answer, since the limit of n plus 1 over an is less than 0, the series, right, you can write a sentence. It's okay.
I remember for a few other tests
we were writing the sentence because we had to. There was way too many conditions and things. Okay. We did not write the sentences for geometric. We did not write sentences for p-series, right? And over here, calculation is clear that at the end you're getting numbers smaller or bigger than 1. So, there are a few of these tests that we really don't need a sentence, but comparison test needs a sentence. The alternating integral test, right? Some of these long, painful methods, right? Because they just have way too many things happening at one time, and you just have to mush them all into one answer, right? Over here, yeah, we got the number smaller than 1. We're good. Just like p-series, right? P-series, value bigger than 1 converges. There's no reason for extra explanations. Okay. They ask me if I want cookies. Of course I want cookies. They're asking for 3 years now. No cookies. I sign up every time. Would you accept cookies? Yes.
I just want to know if you would accept them.
I know. At this point, I just think like I'm statistical data here. It's like if we as a company are to offer cookies, would they actually take it? So we have this one guy who constantly. so let's wait for him to retire and then we'll. 2 years. Okay, let's take a look at some of the cool problems. Lock the doors. Let's go. I mean, you can't go wrong with any of these problems here. Whatever, right? You don't even have to do anything. You can just look at it, right? This one, okay. That one, you don't even bother, right? K to the k, that's rising faster than k factorial. This one is going to die by divergence test, right? You don't even have to crank the ratio. But look at this beauty over here. Look at that. Amazing. Oh, do you remember when you had to convert the values into a sequence first and then do the problem? Yeah, that's around. So a lot of cool problems that you can... Wait, hold on. Can't we do integration by parts here? Yeah, talk about overkill, right? But, right? I know, it's awesome. Like the things you can do. So let's see some of these fun problems and see what's up. Do they have more on the other side? No, that's a root test on the other side. Okay, fine. All right, let's pick something non-threatening to start with. N squared divided by 4 to the n. Because this will be the first one you do on your own, right? So take an plus 1. I'm going to review. quiet. I don't like it. And talk to people next to you. You know that, right? It's okay. The solution is up. Hopefully it matches. Okay, let's try something spicier. And then we're going to do the root test after this example, and we are done with the, we'll take a break. So this one not easy, but we can deal with it, especially because the way these things work. So here we go. We start. Oops, no equal there. We start with an, which is clearly n factorial, everything squared divided by 2n factorial, right? That's. We have to work out an plus 1, and that's going to have some algebra to clear up. So we have n plus 1 factorial, everything squared, divided by 2 times n plus 1 like this, and then everything factorial. So we peel off n plus 1, and we still have n factorial squared, and n plus 1 also gets a square. Is that green? Right? So each one gets a square. Now, in denominator, we have 2n plus 2 factorial when I distribute. Patience. I will work my magic. So now I see that the difference between the old denominator and new denominator are the two terms here, right? That I need to get rid of. So this one, now an plus 1 is going to be n plus 1 squared, n factorial squared divided by, and I am peeling off 2n plus 2, 2n plus 1, and then 2n factorial stays. So I am peeling two terms off because I had a plus 2. So when I peel off the one term, then I peel off the next term, and then 2n factorial. So now I am ready to work out the limit. I have n plus 1 squared times n factorial squared divided by 2n plus 2, 2n plus 1, 2n factorial times flip of an. I'm skipping a step of writing everything 15 times of n factorial everything squared. So now 2n factorial kills 2n factorial. N factorial squared kills n factorial squared. And I just have to deal with this, which is a quarter, which is less than 1, and converges by ratio. There we go. For the limit, usually you just have to look at the leading term with the highest exponent. The leading term on the first one is n squared, and the leading term when you multiply 2n times 2n is 4n squared. So n squared over 4n squared is just 1/4. So you just look at the leading terms. You don't have to go through. I mean, you can FOIL everything and then divide by n squared. You can go through all that stuff. So that is ratio test. Your job is to create an plus 1, work out the algebra around these things, and then finally take this limit and be done. Now, some of these problems you can eliminate with the what do you call it? The test, divergence test, right? If you get, let's say, 2 to the k divided by k to the 99. Yeah, exponential on top, polynomial on the bottom. Exponential is faster. Limit is infinity, not 0. Therefore, diverges. By divergence test, you don't even have to bother ratio. The next test is, and the last test we learn in chapter 10 is the root test. Test number 10. Root test. And you will use this test when your an is raised to the nth power. So the problem will look like this. Let's say 1 to infinity, an, everything raised to the n. So what you would do is you would take the nth root of an to the n, and these will be absolute values, obviously, because then these guys are going to cancel, and then you're just going to have an without that n. So the limit of an in this case, actually, you know, I'm going to write the whole thing. There we go. N goes to infinity. Will spawn one of the three answers, and they are the same as ratio.
We don't have that. Yeah, formula is different. We don't have that n.
Yeah, I understand, but it's going to be easier if you'll see when you start solving problems. So less than 1, converge, more than 1, diverge, equal to 1. Yeah, they only have an there. I put that n so you can actually see it. So you can do either way, but you will recognize the problems because they are going to have everything raised to the n. What's the first problem we're going to try? Obviously, we're going to do a geometric problem. 1 to infinity, let's say 1/4 to the n. You see, this is why I said 1/4 to the n, and you see that n on the top. So the limit, nth root of 1/4 to the n, as n goes to infinity, when these guys completely cancel, you are just going to get 1/4, which is less than 1, convergence by root test. Now you know this convergence by geometric, right? But here is the convergence by root. Summation of, let's say, 6 to the n. What do you know about this one? Divergence by geometric, right? Or divergence or whatever. Now you have nth root 6 to the n. They will cancel again. And you just have the limit to be 6 more than 1 diverges by root. So now you have divergence by root, divergence by ratio, divergence by divergence, and divergence by geometric. Right? Can't miss it. You're bound to know one of the four, right? So let's see some of the book examples. 2n divided by n plus 1, everything raised to the n. So now you understand an to the n, right? Why I wrote it that way. It's just important to have this thing, so you can kill it with the nth root and then take the derivative. Take the limit. Yes.
Should we write an to the nth power on the sheet?
If you want to. You will always recognize root test because the whole problem is always raised to some type of n. So if you want to write it to the on the sheet, write whatever you like. What's the verdict? Diverge. Limit is 2, right? Bigger than 1, diverge, immediately diverge. So we take the limit, n goes to infinity, nth root of 2n over n plus 1, everything to the n power. Root kills that. And we just have 2 bigger than 1. Diverge by root test. Let's see something more interesting, like lock the doors. This one. 1 plus 3 over n raised to the n squared. right, let's take a look. So when we set up the limit n goes to infinity of the nth root of 1 plus 3 over n, and I was going to say n times n, because one of the n's is going to die, right? So we have the limit n goes to infinity of 1 plus 3 over n to the n. So what's this limit? Everyone should know this limit. You learned it in Calc 1. We did it in Chapter 7. E cubed, yes. More than 1. Diverge by root. I'm going to write it again. But every time you don't answer this in this class, a piece of me dies. Here in blood. Limit n goes to infinity. 1 plus a over n to the bn is e to the ab. Makes also cool tattoo. It's like a diagonally across the back. All right, so that's it. I hope you're not disappointed. You've seen all 10 tests. The next section, which is 10.8, which is the last section, is going to be one of those when we pull the page of the book on the screen and you guys, and we discuss which test is appropriate to do that problem. Now, the most valuable problems in your book are the problems where they say choose your test. So in this, every version of the book always has these review portions within the problems. So this is actually root and ratio section in the book, but it has choose your tests and it has all of the tests in there, right, from before. So no matter which edition you use. And those are really good for you to practice. So there is, a whole bunch of them right here. So you see these are only root tests, these are only comparison tests, but this is choose your test. And everything is here on the pile. So let's take about 200 seconds break and then discuss these problems and then maybe start chapter 11. Have fun.